Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list published on August 8, 2025, just 3 days ago. This paper introduces a method that cuts down inference latency by a whopping 43.5% while maintaining competitive accuracy on tough coding benchmarks. The paper is titled Pruning the Unsurprising, Efficient Code Reasoning via First Token Surprisal, and the implications for model training and efficiency are really significant. It achieves this by teaching models to generate much more concise reasoning paths, essentially pruning away the predictable, less important steps in their problem-solving process. Also, the authors shared their official repository for this work, and it's quite comprehensive. If you check it out, you'll find the full implementation for their ASAP framework, including scripts for pruning, fine-tuning, and evaluation. They've even released the fine-tuned logic coder models so you can experiment with them directly. On Hugging Face, you'll find the 7 billion and 8 billion parameter logic coder models. Both pages include usage examples to help you get started with code generation. Alright, to make this concrete, the authors provide a great visual. Here, the original chain of thought is over 1,000 tokens long. You can see it considers multiple redundant approaches to the coding problem, which are these branches that get pruned. After applying their method, the result is the much shorter version at the bottom. It keeps the essential logic to solve the problem efficiently, but cuts out all the unnecessary exploration, going from over 1,000 tokens to just around 200. So how does this all work? Well, this diagram shows the complete framework, called ASAP. It starts with a coarse-grained pruning stage, where a simple, direct reasoning path guides the trimming of the original, complex chain of thought down to its core logic. Then, it moves to a fine-grained refining stage. Here, the system uses a clever metric called First Token Surprisal, which measures the logical importance of each step, allowing it to discard predictable or redundant ones. Finally, this highly efficient reasoning path is used to fine-tune the original model. Moving to the results, this table details the performance of the DeepSeek R1 Distill QN7B model. It compares ASAP against other methods across several coding benchmarks. You can see in the bottom row that the ASAP method consistently achieves the best balance. It gets top accuracy while using fewer tokens and having lower latency. On the challenging live code bench v4v5 test specifically, it significantly outperforms every other approach, including the next best method, Spirit, in both efficiency and accuracy. To really prove why their two-stage approach works, the authors then run an ablation study. An ablation study is an experiment where you systematically remove components to see how much each one contributes. This table lays out the results. The full ASAP method at the top clearly shows the best performance. Notice that removing the coarse-grained stage causes latency to jump significantly, while removing the fine-grained stage makes the accuracy drop quite a bit. This demonstrates that both stages are essential and work together for the best results. So to wrap things up, the key insight here is that by intelligently pruning reasoning paths, especially using this idea of first token surprisal, we can create models that are dramatically more efficient without sacrificing their accuracy. This work really highlights a promising direction for building powerful and practical large reasoning models. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.